A standard data ingestion pipeline for representing documents may consist of several stages: a PDF parser, document layout detection, a chunking strategy, and a captioning step. There are two problems with this approach. The first is that everything needs to be text, losing visual representation. The second is that processing documents in this way is slow and expensive, which makes your RAG pipeline, well, sad. This is where ColPali comes in. ColPali is a novel model architecture based on vision language models that can index documents purely from their visual features. This means that by leveraging this paradigm in your RAG system, your offline document processing is much more efficient and the quality of your retrieval is better. Don't cry, frog. Things are okay. So the goal of this video is to cover what you need to know as an AI engineer building a RAG pipeline. I'll cover the general architecture of this model and how it works conceptually. For excruciating detail, I always recommend reading the actual paper, link below. So, starting with our standard model for document processing. You have a document, which goes through a document processing pipeline and produces embeddings. These embeddings are then stored in a vector database to be queried at a later time. The dotted purple line is the offline document processing phase in the original diagram. Once we've stuffed our vector database with all of our document embeddings, we can now do online retrieval. Online as in serving document embeddings for each user request. Let's say a user asked our RAG system the question, what are VITs? We can process this query using a text embedding model to produce query embeddings. Sweet embeddings. Note that the model used in the offline processing step to produce embeddings of documents is the same model used for producing query embeddings. This is because both query and document embeddings need to be in the same embedding space. Now we ask the vector database to give us its embeddings. We then compute what's called a max sim. Basically, for each query embedding, we compute its similarity with all of the other document embeddings. We then take the max score, then produce a set of the most similar embeddings, which will then be used as context to the language model. This is your standard RAG. Query goes in, we get relevant documents back. The language model uses the query plus relevant documents to give us a response. And if you're like me and also think vision transformers are awesome, like and subscribe for more. ColPali replaces the purple dotted module from our standard processing pipeline with a visual document understanding module that is capable of producing higher quality embeddings more efficiently. First, a document is processed by a vision encoder, in ColPali's case, SIGLIP SO400M. This is a clip-like model that produces embeddings that map to image patches in the document. I won't get into the details of how this works, but the gist is, you pass the vision encoder an image, it's going to give you back embeddings that correspond with image patches. These image patch embeddings are passed to a linear projection layer that allows the SIGLIP model's output embeddings to be fed into Gemma 2B. If you're familiar with PolyGemma, this will start to ring a bell, because it's exactly PolyGemma. The first part of ColPali is indeed PolyGemma 3B. ColPali extends PolyGemma. If you're not familiar with PolyGemma, the general idea is taking the SIGLIP vision model's output and a sentence piece tokenizer output and concatenating both embeddings to be fed into Gemma. I highly recommend checking out the full paper, link below. The output of PolyGemma is then passed through another linear projection layer that reduces the embedding dimension for lighter weight storage. This is part of ColPali's optimization of the data ingestion pipeline. Finally, ColPali image patch embeddings are produced. Image patch embeddings are stored in a vector database like before. And the same sort of retrieval happens. Note that since PolyGemma is an extension of Gemma, we use Gemma as our language model for both the document processing and online processing. Finally, we compute the max sim like we did before, producing the most similar image patches that map to our input query. To recap, ColPali produces higher quality embeddings more efficiently by leveraging a vision language model to exploit the rich visual cues in documents. There's a slight overhead in the online processing phase, which is nominal compared to the gain in retrieval quality and offline processing performance. If you made it this far, give yourself a pat on the back, like and subscribe, leave a comment, and keep building amazing things. Until next time, cheers.